Now we will learn how recurrent neural networks work. An RNN, recurrent neural network, is a type of neural network used in machine learning that is especially suited for processing sequential data like time series, text, and audio. So RNN or recurrent neural network is more suitable for continuous type of data where we have time series like stock prices or house prices, prediction of house prices or stock prices, and text processing like summarization of text or conversion of text from one language to the other, or something, or text generation, or audio signal, speech signal processing. Unlike traditional neural networks, RNNs have loops that allow information to be passed from one step of sequence to the next. Here in RNN we have got the concept of feedback, that the previous output will influence the next output. As we know in feedback systems, when if we have got an output, then that output will influence the next input. In a similar manner, in RNN, the process output of dense layers is influences the next input of the process. This makes them a good learning patterns where past information is important for predicting future steps. At each time step t, an RNN takes input vector xt. Input vector xt means, for example, if we assume that we are talking about text, then for example we have got a word I, then what we will do, that we take the embeddings of I as an input, then that is at our time step, say t is equal to 0, and then next we'll have t is equal to 1, then I will say that we'll take the next word, then at t is equal to 2 we'll take the next word. So at every time step we take each word as an input. And then at dense layer we have previous hidden state ht minus 1 computes the current hidden state ht. So ht is what? Is equal to tan h wxh xt plus whh ht minus 1 plus bh. This tan h hyperbolic tangent is the activation function which is used to make the output nonlinear. Here you can see that this part, if we just ignore this part whh ht minus 1, if you ignore this part, then this part wxh xt plus bh is as same as we have used in CNN and FNN and many other machine learning algorithms. The only thing we can see is here this addition of whh and ht minus 1. Ht minus 1 is actually indicating the previous output of h. Optionally, an output yt is produced. Yt is equal to x why ht plus by. So this output is very much similar as we have seen. This is exactly the same one as we are seeing over here. The only difference is that we do not have this previous output in this one, in this output. So xt is what? The input vector at time step t, for example a word or sensor reading. ht minus 1 is what? Hidden state from the previous time step, and wxh is the weight matrix for the input xt, means whh is the weight of the previous output h, and bh is the bias vector. And tan h, as I explained you, the hyperbolic tangent is activation function applied element wise, and the purpose is to make the output nonlinear. So at each time step t, the RNN looks at the current input xt. It also considers the previous memory ht minus 1, as I just told you. It combines them wxh xt plus whh ht minus 1 plus bh. So this previous output is added into this wxh xht and plus bh, but we do not add this previous output as it is, but we multiply it by a weight. So the certain percentage of previous input will be added. For example, the previous, whatever the value of previous output was, h was, if I multiply it by WHH, say it is 0.5, means only 50% of that value will be added into this WXH XT plus BH, and then applies 10H to add non-linearity. This produces a new hidden state HT. So input at current time step, let's say at time step t, the input is vector x, xt is equal to x1 and x2, and previous hidden state is from the last time step t minus 1, we have a hidden state xt, ht minus 1, h1 and h2. Multiply input with input weights. We simply multiply the input with input weights, as we have seen in CNN and FNN. So every input, this x1 is multiplied by x11, and this x2 is multiplied by x2 12, x21 is multiplied by x1, and xw2 multiplied by x2. I will explain this multiplication in more detail. So multiply previous hidden state with hidden weights, and WHH determines how much the previous hidden value will affect the current one, as I told you, and then we add bias vector as we have done before. So we get this z, and then we take 10H of this z, this output of WXH XT plus WHH HT minus 1 plus BH. Simple RNN is called vanilla RNN, and usually it has got only one hidden layer. This layer is used across time steps. Even though there is one layer, it is unrolled across time when processing sequences. So you can think of simple RNN as deep in time but shallow in layers. You can stack multiple RNN layers on top of each other. The output of one RNN layer at each time step becomes the input to the next layer. You can have multiple layers as well. Commonly, we have got 2 to 3 layers in RNN. More than 4 layers is rare. Each hidden layer has a number of hidden units or neurons, which defines the dimensionality of hidden state edge. As we know that when we say units or neurons, actually it is the place where we apply the function. This is called neuron. Application of function, whatever function we have, as we call it neuron. So common choices are small models like 32, 64, 128 units, medium models 256, 512, and large models 1024. Now we are going to consider a simple example of classification, mood classification. And suppose the input is I feel happy. Goal is that RNN process each word step by step. We have to classify whether the mood is positive or negative. For final hidden state is passed to a softmax layer to classify positive and negative. This is again one hot coding where all other values are 0. For positive, this one is 1, the first index of the array, and for negative, this second index is 1 and other is 0. The first one is 0. So if we get a value greater than 0.5 and close to this one, then it means the mood is positive. And if we got this one is 0, first one value is 0, and the other one more than 0.5 and close to 1, then it means it is negative. So let's consider an RNN architecture where input dimension is 3, means we are getting 3 inputs for each word, 3 embeddings for each word. Hidden layers 2, neurons per hidden layer are 2. We are using 2 hidden layers instead of 1, and we are using 2 neurons per hidden layer. Here we have limited the number of neurons. We are not using 32 or 64, just 2 neurons to show you how this works. And output is final hidden state. So this is the network we are considering over here. This is our input x0, x1, x2. These are the embeddings of, for example, say first word like I. So I has got, as I have shown you over, they have got input dimension 3. Input dimension 3 means we have got three values, embedded values of I, three embedded values of feel, and three embedded values of happy. So first embedded value x0 will be here, second one will be here, and third one will be here. Then we input that one to this neuron, this first one. This one shows that this is the first layer. So it 1 1 and 1 2. This second 1 and 2, they show the number of neurons. So 1 1 means first layer first neuron, and here it means first layer second neuron. This means second layer first neuron, and this means H22 means second layer second neuron. When I input this value x0 over here, this will be multiplied by W, and you can also see that these all the values are connected with each other. This is the typical behavior of any neural network. This output x0 will be input to this neuron and this neuron both. Similarly, this one will be input to this one, and this input will be put into this neuron and this neuron both. So for this neuron, this one, how many weights should we have? Should have 3 weights, each weight for each input. One first weight for this x0, second weight for this x1, and third weight for this x2. And WHH is what? WHH is simply the weight which we are going to multiply with this HT minus 1, means the previous value of H. And it will give us two outputs. One will be placed over here, the other one will be here. And you can see that the output of each layer becomes the input of next layer. So the output of the first hidden layer will be the input of the next hidden layer. Now I talked to you about embedding, but I have not explained you what embedding is. Before we continue with the example, let's understand what is embedding first. Embedding captures the semantic meaning of the tokens or words and convert them into numerical vectors. For each word is assigned an ID known as token ID. First of all, what we do is that we assign an ID to each word. These words are meaningless for mathematical computations. The embedding matrix maps each token ID to a dense vector, a list of floating point numbers that captures the semantic meaning of the token. Consider these two sentences. I deposited money in the bank. We sat at the bank of the river. The word bank has different semantic meanings in each sentence. So what does semantic means is that a word may have multiple meanings according to its usage. The word bank has two meanings. For example, one is the bank, the office where or the institution where we go and we deposit money or we withdraw money, and bank also means the side of a river. So here the word bank has different meaning. I deposited money in the bank. This bank is different from we sat at the bank of the river. So how a computer will know this bank is different from this one? From its usage or from its surrounding words. So in sentence 1, bank refers to financial institution, and in sentence 2, bank refers to the side of river, geographical meaning. There is another example. Only he loves Pakistan. No one else loves Pakistan. That's what it means. Only he loves Pakistan. And he only loves Pakistan means he loves no one else, but he only loves Pakistan. The sentence is very much similar. Both sentences are similar. The only difference is where you have placed this only, and it has changed the meaning of the sentence. When we have to do things like mood classification, then we have to see where and how that word is used, where we have to see whether it is used in positive meaning or sarcastic meaning. So the word only changes the meaning of the sentence based on its position. Consider the following sentence. All the students passed the exams, and the students passed all the exams. Though both sentences contain the almost same words, the meaning changes due to the position of the word all. In sentence number 1, all refers to the students, and in sentence number 2, all refers to the exams. So for example, the word bank in I deposit money in the bank is different from we sat at the bank of the river. So embeddings for these both sentences will be different. The sentence I love AI, first we take the tokens I love AI. Each token is assigned a unique ID. For example, I have assigned 10 to I, 25 to love, AI 204, and this full stop 2. Each token ID is converted into a dense vector using an embedding matrix. Suppose embedding dimension is d is equal to 4. Then, for example, for this one, our embedding vector is 0.1, 0.2, 0.3, 0.4. For 25, it is 0.5, 0.6, 0.7, 0.8. Of course, it is just for the example. We don't assign word like this. The token IDs are converted into token embeddings by replacing tokens with embedding vectors, such as 10 is replaced by 0.1, 0.2, 0.3. So this is what determines the dimension of the input. How many, especially when we are talking about this text, in context of this text processing, like this classification of mood. So the number of inputs depend on the embeddings, the number of embeddings. So this is what the purpose of embedding is, that to understand the semantic meaning of each word in the sentence. So suppose in our example, we go back to our example where we have to classify the mood. We have got the input sentences I feel happy, and for that we have embedded like this 0.1, 0.0, 0 and 0.3, 0.0, 0.2, 0.1, and happy is 0.4, 0.1 and 0.0. It is random. It is just to show you how the computation is done. It is not really, we have not taken the actual values. So since we have got 3 embeddings for each word, so our input size will be 3. The input dimension is 3, and since we have got 3 inputs for each neuron, we need 3 weights. So this, for example, this 0.5 is for x0, but for the first neuron. Minus 0.2 is for the x1, and this is for x2. This is for first neuron, and 0.8, minus 0.6 and 0.1 are for the second neuron. What do I mean first neuron and second neuron? Recall that in this figure we have got 2 neurons in the hidden layer. So first array of weights was for this neuron, where each value of W corresponds to x0, x1 and x2, and the second value of neurons was for weights was for this neuron. Similarly, we have got WHH 0.4, 0.1 and minus 0.3 and 0.6. Each neuron we have got 2 outputs, so it is 0.4, 0.1 and then minus 0.3 and 0.6. For the second layer, you can see we are using only 2 weights, not 3 weights, because as you can see that in second layer we are getting output from 2 layers of the first hidden layer. So we need only 2 weights. I think it will be easier for you to understand if I explain it with the help of the figure. So this actually, this 0.6, it will be used here for the input from here, and this minus 0.1 will be used for the input from here on this neuron. Similarly, we are getting 2 inputs, one from here and one from here on this neuron. This 0.2 will be multiplied by this input, and this 0.5 will be multiplied by this input, and this 0.5 and 0.3 will be used for each H values from this one and this one, which will be multiplied, used when we will process it. Then we use the previous value, then we will multiply this previous value with this corresponding weights, and here also we have got 2 weights, because on each neuron we are getting 2 inputs. Finally, we get WHY and we multiply with their weights. Again, you can see here easily that we have got 2 inputs on each neuron with the same idea, and then we add the bias. So as I told you that we enter the word one at a time, at time stamp or time step, whether you call it time stamp or time step, doesn't really make difference. So each time step for example, the first time step we have got 1, on the second time step we have got feel, and then third time step we have got happy. We want to start index from 0 or 1, doesn't really make difference. It is one and the same thing. The only thing is that we do it step by step. So At t is equal to 1, if I am starting the time step with 1, xt is equal to x1 is equal to 0.1, 0.0 and 0.3. This is what we have assumed in the beginning, that this is the embedding of I. The embeddings for I are 0.1, 0.0, and of course when first time we will input this value at t is equal to 1, there will be no t minus 1, it will be 0. So we have assumed t minus 1 is equal to 0, 0. And h of t is nothing but tan h wxh 1, 1 denotes the layer, xt plus whh 1, ht minus 1, 1. Since we are talking about t is equal to 1, we are starting with t is equal to 1, so t will be replaced by 1 in this equation, and h1 is equal to tan h x w xh 1 into x. What is the weight xh? We have assumed it previously. It is 0.5 minus 0.2 and 0.3 for the first neuron, and 0.8 minus 0.6 and 0.1 for the second neuron of first layer. And then we multiply it by 0.1, 0.0 and 0.3. X is our input, and this is our WHH, but it will be multiplied by 0, 0, because initially the value of H0 is 0. So it will just become 0. So since this one has become 0, we multiply this one by this one, simple matrix operation. So we get 0.14 and 0.11. Then we apply this tan h function on this output, and we get 0.1390 and 0.1097. Now this output will be passed on to the next layer of the hidden layers, second hidden layer. And as I told you before, that the input of the second hidden layer will be actually the output of the first hidden layer. So as you can see over here, that I have assumed that x1 is 0.1390 and 0.1097, because this is the output of our first hidden layer, which becomes input of the second hidden layer. And here the weights are the same as we have assumed before, and then we do the matrix multiplication by these values, and again these values will become 0, because again h t minus 1 is still 0, because it is t is equal to 1, and finally we get the values h12 is equal to this 0.07229 and 0.08245. So this is the output of two neurons of second hidden layer. Actually it would have been better if I would have computed the output here as well, but I have just skipped it for the moment. In actual when we will do this learning process, we will see the steps more accurately and more in detail. Here I have not added the value of bias as well, because we have assumed the value is 0. So but it should be added, the value of bias should also be added. But I'm just here I want to explain you how the input is placed or is processed in time step 1 by 1 in the forward process. So when t is equal to 2, now our input will become field, and now we will take the embeddings of the field. Now as you can see, x2 is equal to 0.0, 0.2 and 0.1. These are the embedding values of field, and our previous hidden state values were 0.1390 and 0.1097. Now here you can see that we are going to use the previous hidden values. Before we had used 0, 0 for previous hidden values, but here we are not using 0, 0, but the output of the hidden layer in the last time step t is equal to 1. In t is equal to 1, at h1 we had got this output 0.1390 and 0.1097. So as you can see over here, these are the weights. The weights are the same. The only thing which has changed now is this input. So this value is now 0.0, 0.2 and 0.1. Again the weights are the same, but here instead of 0, 0 we have got this previous value of h, and after doing the matrix multiplication we get the output 0.0565 and 0.13412, and after applying tan h we get these values. So this is the output of our first layer at t is equal to 2. Here this t h2 representing t is equal to 2 and 1 is for our first layer. Now this will become the input for our second hidden layer. So here, as you can see over here, this h2 1 has become our input. So now the weights will be the same. The output of the first hidden layer has become the input for this one. Again the weights are the same. Now these are the values of the previous hidden value. Again we simply apply the matrix multiplication and we get the output h22 is equal to 0.08126 and 0.0106. This is t is equal to 2 and for second layer of hidden layers. Similarly, then we apply t is equal to 3 for input happy. Now I think it should be clear to you that this is a embedding of happy 0.4, 0.1, 0.0. These are the values of h21. Now we are going to, in t is equal to 3, we are going to use the values of h2. In h1 we use the values of h2 we use the values of h1. In h1 we use, there was no previous value, it was 0 0, and now we are using the values of h2 in t is equal to 3. Again the weights are the same, embedding values for happy, and this the weight, and this is our output of the previous value at t is equal to 2 for first layer of the hidden layers. And again h31 is equal to 0.21256 and 0.31217. Now with this output of the first hidden layer will be passed to the second hidden layer. Again similarly we apply the values. Here this is the value of the first hidden layer, this is the value from the previous t is equal to 2 of the values of the second hidden layer. And then we again get h32 is equal to 0.1627 and 0.23627. And as I told you that we had to apply add this bias in each one of them, but we had assumed for the simplicity of the computation that all biases are 0. Now we simply, the application on output is very simple. We simply apply the regression equation and we get z is equal to minus 0.6 and minus 0.69. Now we apply softmax over here. We do not apply sigmoid because here we are applying multiple classification. In case of multiple classification we use softmax instead of sigmoid. Sigmoid is for binary classification. So exponentials of large positive values can cause overflow and large negative values can cause underflow. To avoid this and improve numerical stability, we adjust the input vector z. And how do we do that? We simply subtract the maximum value of the vector from each entry in z. So in this one, in this z output, our maximum value is 0.069. We subtracted from each value, so we got minus 0.138 and 0. It will not affect the output of the softmax. This does not change the output of softmax, but it prevents very large small exponentials. So now when we applied this one, we finally got 0.4654 and 0.5346. As you can see, 0.5346 is greater than 0 and its value is more close to 1, so we can say that the output is 0 1, which means it is negative according to our assumption. Although the sentiment or the mood is positive, but here we are getting the incorrect result and we are getting 0 1. The main reason is that the values which we have assumed or weights which we have assumed are arbitrary. They are not trained values. If we had used trained values, then of course we would have got the correct answer. So anyhow, we have seen how this works, although the result is not correct, but we understand that how this process of forward pass works, or how the prediction works. But now we have to see how the training is done. Training is a little bit different from the previous ones, just little difference because of this previous value of h. Here we have to use time step, so it is little bit different from CNN and FNN. I will not explain you the forward pass because I've already explained you in detail how this forward pass works. I will just show you how I'm going to use it in this RNN architecture. The RNN architecture is very much similar as we have shown you before. The only difference is that here I am using 4 inputs instead of 3. Means in embeddings, for embeddings I am using 4 values rather than 3 embedding values. Does it make any difference? No, it depends on the embedding algorithm which you have used. Again, I am using the same I, feel and happy. The only difference is that now I am using 4 embeddings. So you can guess that I am going to use x0, x1, x2, x3 instead of just x0, x1 and x2. We initialize all hidden states to 0 as we know, and h1t hidden state for hidden state layer 1 at time t. So here I'm using a little bit different notation. This h1 means this is first layer, this is h2 means this is second layer, and t is for time step. Here we are using time step 0, and as I told you, it doesn't make any difference whether you start with 0 or you start with 1. In this example, I'm going to start with time step 0. So for z1 0 means that this is for first layer and time step 0. wxh1 into x0, wxh1 into h1 minus 1. We get minus 1 because 0 minus 1 is equal to minus 1. So the process is very much same. In first layer, in the first time step, we use all the weights. What is the value of embedding value of I? This is the value of I, and this is the weight of hh, but we multiply it by 0. And as I told you that we didn't use this bias before, now we are going to add this bias as well, which is initially 0. So this bias is 0. Simply matrix multiplication, and we got again 0.08 and 0.012. What I mean again means again we have got only 2 values of output of the first neuron of the first layer. Now these outputs 0.08 and 0.12 will be fed to the second layer neurons. But before that we apply 10h and we get 0.0797, 0.1194. Now these are the weights of the input values from the first layer, and these are the weights which we are going to apply on the previous value. But since it is the first time that we don't have any previous value, h minus 1, so it is 0 0 again, and this bias is also 0 0. h20 is equal to 0.02787 and 0.0. And as I told you previously, we didn't compute the output for each time, but here we are going to compute the output as well. So for t is equal to 0, our output is 0.02109 and 0.03302. So at t is equal to 0 means first time step we have got the output. We have got the output of first hidden layer, and we have got the output of the second hidden layer. Now we will use these values, these outputs in the second time step. At t is equal to 1, now we will input field, and now we have x1 is equal to 0.5, 0.6, 0.7, 0.8. Here x1 actually is not the neuron number, it is indicating this second input. Otherwise the number of neurons at the input are the same, x0, x1, x2, x3. So don't get confused with this x1 with this embedding x1. This embedding x1 is different, and this x1 is representing this field over here. And again we do the same thing. Our weights are the same. We simply multiply it with this input. X1 is this one actually, this input, and we get the output 0.24 and 0.28. At hidden layer 1, our weights are 0.1, 0.0 as we know. Now here we have got this H10 because as I told you in the second time step, we have the H10 is not 00 because we have computed H1 before. So the previous value of H will be used, which we have used over here, and this H11 is not multiplied by 00 anymore, but it is multiplied by these values. This is the output of S1. So what will be the total output? BH1 is still 00, it is not updated yet, we are training, and initially we have assumed 00, so it is still 00, we have not updated it yet. And finally we apply this H11 on this Z11, which is this value, after adding these two values, the output of this one and this one. 0.24 is added to this one. This is the output of this one, and this is the output of this one, and again this is the output, second index or second array element value of this one, and this is also second array value. So finally we get H11 0.243, 0.284. Now the output of the first hidden layer becomes input of the second hidden layer, as we have done before. Recall that H20 is what? 0.02787 and 0.3183, and also we have got H1 is equal to 0.243 and 0.284. Now we will use the previous values which we have computed in t is equal to 0. So finally we get the output of hidden layer 2 is 0.0782 and 0.0825. I have not explained you this step by step over here because I have explained you multiple times before. So I hope that you already understand how we have got these values over here. Although I have shown you the work over here, if you want to understand it, you can pause the video here and you can try to compute it. And if you don't understand it, then go back to the example, the first one, in which we had explained you the forward pass process, and from there you can get it how we have got these values. Output layer is very much similar. Again, WHY, the output of the second hidden layer becomes the input of the output, and there we have to simply multiply it with the corresponding weights, and then we have to add the bias, which is in this case initially is 00. So we get Y1 is equal to 0.0564 and 0.0884. As you can see that we are computing output at each t time step in this example, unlike before where we did not compute the output at each time step. And then for t is equal to 2, happy, we do the same process. So finally we get H12 is equal to 0.400 and 0.437. And for the second layer, H22, for second layer on of the second layer, we get 0.127 and 0.131. Now again we compute the output, and output is 0.0903 and 0.141. Now this is our predicted value. Finally y2 is equal to 0.0903 and 0.141, and our two values are 0.1 and 0.2. Now we will do the back propagation through time. For that, first of all, we have to compute the loss, which is LT is equal to half into sigma y true minus y prediction and squared. So we will compute the loss at each time step. As you can see that we have computed the output at each time step. So this is the predicted value at L0, 0.0211 and 0.033 and 0.0564 and 0.0884 at L is equal to 1, and 0.0903 and 0.141 at L is 2, or T is equal to 2. So we finally got these three values. So we will just, to get the total loss, we will just add these losses at each time step. Whatever the loss we got, we will add them up, and so the total loss is 0.0261. Now backward pass starts. This is also again very much similar to CNN, but we have to do it at T is equal to 2, T is equal to 1, and then T is equal to 0. We start from T is equal to 2 from the final one. So output gradient, what's the value of output gradient at T is equal to 2? It is simply delta LT delta WHY YT minus Y2 Hadamard process, which is simply the multiplication of the two array values or matrix values and with corresponding elements, and 10H derivative of 10H with respect to ZYT, and H2 T2. T, the capital T is the transpose and small t is the time step. And we know that 10 derivative of 10H is 1 minus 10H square of Z. So we don't have to compute the derivative. We will use this equation. 10H derivative is equal to 1 minus 10H square Z. And for hidden layer, our equation is very simple. We'll apply the YT minus Y2 multiplied by HYT, and then apply the Hadamard with this derivative of 10H and multiplied with by H1T. So it looks a bit difficult and very confusing over here, but when we'll apply it, you will find it very simple. It is not that difficult. It looks difficult, but it is not difficult. So we start the propagation with output that we got at T is equal to 2. So what was the output at T is equal to 2? 0.0903 and 0.141. We simply find the Y2 minus Y2, which is this one, and this derivative is what? It is nothing but 1 minus Y2 square. So what we do is that the output at each, for example, we have got 2 neurons, so first we'll square this one and subtract it from 1, and then we'll square 0.141 and then subtract it from 1, and we get this, the output for 2 neurons. Now we know what is that H2 is equal to 0.217, 0.131, which we have computed before. We just plug in the values in this one. So we already have this one, we already have this one, we have this one, and we have to plug in the values. So as you can see that this is Y2 minus Y2, which we have computed over here, this one, and this 10H, this also we have computed here, so we have put it over here, and this one we already had computed before, so this is here. So first of all, what we need to do, we find the Hadamard value of this one, multiply this one by this one and this one by this one, so we get the Hadamard value, and then we do the matrix multiplication. After this matrix multiplication, we finally get minus 0.0012 minus 0.0013 and this value over here. So this is after this matrix multiplication of these two vectors. Now we have to compute the hidden gradient at hidden layer 2 for T is equal to 2. Remember that we are doing all this for T is equal to 2 at the moment. Again, all the things are same as we have seen before. The only thing is that we have to plug the values. What was the assumed value? We wait for the HY. It was 0.3, 0.4, 0.5, 0.6. We are training the values of weights, so we have to use the current values what we had assumed. So this is the assumed value of weight, and we simply multiplied by Y2 minus Y2. So as I told you, this T is for the transpose, so this is the transpose of 0.3. This is the value, and we are going to take the transpose. After taking the transpose, we got 0.3, 0.5, and 0.4, 0.6. You can see this 0.3, 0.4 into and 0.5, 0.6 is transposed to 0.3, 0.5 and 0.4, 0.6, and then we multiplied this by 2 minus y true, and we get this is the output of this one. Now again we compute the tan h derivative of tan h, which is 1 minus h2 square. Again the process same, I have not shown here, that we simply took the each value of h22, squared it and subtracted from 1, and finally we get this 0.984 and 0.983. I have not shown the working over here. So delta h2, now we call this whole computation as delta h2, and we got this value is equal to minus 0.0319 and minus 0.0386. And finally we will simply multiply this value with the ht value shown you before, and we finally get this is the gradient at layer 2. Now we find the gradient at hidden layer 1 at t is equal to 2. So now what we have here, we have WH1, H2, 0.2, 0.1 and 0.1, 0.2. This after transpose we multiplied by this y2 minus y1, and then we apply the head mode, and finally we get this minus 0.03. So we already have computed delta h2 before, so we are just simply use the values here, and then we computed 0.2, 0.1 and 0.1, 0.2 transpose of it, and minus 0.0319 which we have computed before, and finally we get these values, and the process is exactly the same which we have used before. We already know the values. Some values which we have computed, I have not shown you the how we have computed, because I have shown you how to compute it, like this one tan h derivative. I have told you how to compute it, so I am going to just either it is computed, I will use it from the previous computation, or I have explained you how to compute it. So finally we get delta 2 L2 of WX H1. Here you can see we have got 4 values. That's what we expect, because we are moving back. At H layer 1 we had 4 inputs. So similarly for gradients T1 and T0 we compute the values. I'm not showing the working over here because I have shown the process is very much same, but what we have done for T2 we will do the same for the T1, and T is equal to 0, and we got all these values over here. Now we update the weights. To update the weights we are using the same formula which we have used in in CNN and FNN, where we have to multiply this gradient by our learning rate and subtract it from our current value, and then we'll get the updated value. So our current value is this is our learning rate. This is our gradient value, the same which we have here, this gradient value. So we simply multiplied by this learning rate and then subtracted from this current weight, and then we get this updated value of WXH1. Similarly we will update all the weights, then we keep repeating the process again and again until we update all the weights. So this is how the training of RNN is done.